Good afternoon, everyone. Welcome at our webinar Cleaning in Place Optimization in Dairy Processing. And in the next coming hour, my colleague Martijn Fox and I will lead you through possible optimization possibilities within cleaning in place. And just to introduce you to my colleagues who will be here today, actually are Martijn Fox, who will be the presenter for the second half of this presentation of this webinar, and also Rien van Heekesen, he was present to arrange all the incoming questions, and I will be the one who is doing the first part of this presentation. So again, welcome at this webinar about CIP optimization, and I would like to start first with what you call the key message. And it's very important before we start talking about cleaning in place to keep in mind that what's very important to know is, and I'm going the wrong way now, is before you start, know your enemy. And what you see on this screen, for example, are various ways of fouling. For example, bacterial fouling, mineral fouling, or protein fouling. And it's very important that you know that you're aware of this type of fouling before you start doing your CIP. So by keeping this in mind, and it will be something to take home for you when we finish this webinar, is the topics we would like to discuss are the following. First of all, I will tell you very short about who is NISO, what do we do and what's our way of working. I will then start with a very short explanation of what types of fouling do we have, what is fouling actually, something about cleaning and disinfection theory, how should we clean, what type of agents should we use, is disinfection, for example, really necessary? CIP design and conditions, what's important when you buy or make a new CIP installation. Cleaning optimization, and that's not only about optimization of the CIP, but also about prevention of fouling. Especially this part will be presented by Martijn Fox. And finally, we will close with a short resume about what we have discussed during this hour. And of course, please feel free, if you do have any questions, our email address is placed on the first slide of this webinar. If you may have questions after re-listening this webinar, please do contact us, and perhaps we can help you with your specific question, or perhaps with optimization of your current CIP installation. Okay. So first about NISO, very short. Who's NISO actually? Well, we are a contract research organization located in the center part of the Netherlands. We're independent, so we are privately owned, and we have no formal connections with government or whatsoever. And we do work for, in fact, the whole food industry worldwide. In total, we have about 200 people working with us, and we have what we call sales offices in France, USA, and Japan. But what's very important for us is that we do not do only research, but what we especially do is that we do help customers in translating the question from lab to practice, but also have an application. So at the end of a project, you should be able to have an application feasible to carry out in your own factory or to scale up further in your own production process. And of course, we do that not only with a lab scale, but we also have the possibility of making or carry out experiments in our food grade pilot plant with various scales with a maximum of 10,000 liters per hour. And finally, we do work under Dutch law, and of course we have all the necessary certificates, for example ISO 9001 and GMP Plus with regard to the feed products we can produce as well. Okay, so far NISO. Now we go back to the webinar about fouling and about cleaning in place. And first of all, and we said of course know your enemy, it's important what is fouling exactly. So what type of fouling is going around in your equipment. And we actually made this overview table in which we have actually four, and we're looking at, let's say, the more protein mineral fouling, 4 different types of fouling. And to start with, you see we have sugar, and of course you all know that it's water soluble and normally pretty easy to remove. But once you've heated it, you have the risk of caramelization, and in that case it's getting more difficult to clean. However, still is, looking at the all 4, one of the easiest to remove during a cleaning process. So for example, in the fruit juice industry, fouling is not that big issue. I know by experience from my previous job. So just a very standard CIP procedure is doing the job quite good. We can now coming to, let's say, the fat and the protein. Fat is, as we all know, water insoluble and more difficult to remove, especially when you have polymerization, and it's even more difficult to remove. And when we look at protein, it's even more difficult to remove, especially when proteins are denatured. So when they have been heated, proteins start to denature, to unfold, and to react with all kinds of components that are in their neighborhood, and they make a very strong and severe fouling layer, especially on stainless steel, and it makes it very difficult to remove. So it's very important to know what type of fouling do you have, because based on that you can determine your CIP protocol. Finally, we do have the minerals that are normally water soluble, but in case they are attached or included in a protein fouling, they are quite difficult to remove. If they're only mineral fouling itself, normally water combined with an acid could do the job to remove it. So concluding, it's very important to know what type of product you're working with, which will result in a different type of fouling, of course. Okay, so far the let's say the more protein minerals. We now come to, let's say, the microbial type of fouling, and also within that category we have, let's say, various classes of fouling. At first, it's very important to know what kind of microorganisms present. And at first, we do have the so-called vegetative microorganisms, so that are the non-spore formers that are mostly not that heat resistant, but they can grow very fast. An example is the thermoresistant streptococci, who are famous to grow very fast in downside regenerators from pasteurizers. And they go that fast that they can even increase in concentration, that you have more at the end of the process than at the beginning of the process. So you get some kind of fermentation process actually in your heat treatment equipment. The second type that can be in your equipment is so-called spores. They are more resistant against heat and against all kinds of chemicals. And very famous ones actually are the thermophilic spores, which are known to be present in evaporators and cause biofouling in biofilms over there. It's important to know, okay, what age is the bacteria? Is it very old? Is it very young? Is it already have had a lot of stress already? So it's important to know if you have a very old layer of fouling or a very fresh layer of fouling, because the older it is, the more difficult it is to remove. And finally, we have the topic of biofouling and biofilms. And what you can see in this picture over here is actually a biofilm. And a biofilm is almost a whole community of bacteria living there, increasing the concentration, detaching to the product, and actually have a whole complete ecosystem in which they can live and can increase the concentration, and therefore also the problems with contamination of your product. Biofouling on itself is more the attachment of bacteria to the surface, and after a certain moment they can detach. So they don't have a whole community with let's say the adding and removal of let's say nutrients or the waste disposal, etc. But you only have bacteria, and for a biofilm you have a whole community. So that's important to keep in mind when you talk about these two issues. Okay, so far about the fouling itself. So once you know who is your enemy, we now come to the cleaning process. And at first, very short, the cleaning theory. And you might have seen this picture before. This is the so-called Sinner circle. And you see that 4 parameters in total determine the total effectiveness of your cleaning process. And the 2 biggest ones are the chemistry and the mechanical energy. And the 2 minor ones are time and temperature. All the 4 I will discuss in the next coming slides, and you will see what will be the influence of, let's say, different chemicals or different types of mechanical energy to the total result of your cleaning process. So to start with the chemistry, we have various ingredients that can be used to do, let's say, CIP cleaning in place. First of all, it's very important to see what is the concentration. It's very important to not increase that concentration too high, because of course it's always cost more money because double the concentration, double the cost of chemicals, but also the effectiveness isn't always increasing as much as you would expect. And for example, for alkaline, it's known if you increase the concentration too much during a standard, let's say, well-designed fouling removal, the fouling layer is swelling due to the chemicals. And if you have a too high concentration, let's say above 1.5 to 2%, then the swelling is going too fast that a certain kind of rubber layer is formed on top of the fouling layer. So the swelling does not take place. And the fact you need swelling to make the fouling layer more vulnerable for the mechanical force. So if the swelling does not take place, it takes much more time to remove that fouling layer from the surface. So looking at lab conditions, normally an alkaline concentration of 0.5% is enough, but we do see in practice that 1% is normally applied and have very good results. Looking at acid, you see 0.6 to 0.8% as applied in industry and doing the job very well. In addition to, let's say, the standard alkaline and acid, you do have other components, for example, surface activant components that will make it easier to attach to the fouling. You do have what we call sequestering agents that can bind specifically to, for example, to calcium. EDTA is a very well-known example of that. And finally, we have so-called oxidizing components, and actually oxidizing components will help, let's say, in mechanical force, because they will form oxygen, which will help in getting more tension and force into the fouling layer, which makes it more easier to remove. So far, let's say the chemistry. Now come to the temperature, and actually for the temperature the same is too high isn't always good enough. Normally, rule of thumb, if you increase temperature, normally with an increase of 10 degrees C, which equals to 18 degrees Fahrenheit, you have a 2 times more effective process. However, for most detergents they say it's effective above 50 degrees C, but if you go above 70 degrees C or even go above 80 degrees C, you do say that you have, let's say, side effects which are less positive for the cleaning efficiency. So therefore we advise always to have, let's say, a cleaning temperature between 70 and 80 degrees C in your CIP tank, because then you know that at least the temperature will be reached in your, let's say, during cleaning that is above 70 degrees C, because that's more or less the rule of thumb to have that in your, let's say, cleaning process. If you go below that, then we do see that the effectiveness is too low. If you go too high, you see, for example, at 80 degrees C, you see an additional mineral deposit, which actually is not wanted. You don't want to have in your process. So actually, as a resume, you see alkaline have a maximum of 80 degrees C, and acid can be a bit lower, let's say 60 degrees C, and of course the Fahrenheit you see behind it in between brackets. Mechanical energy as the, let's say, the third parameter of cleaning. Rule of thumb is that you need to have turbulent flow. And turbulent flow in, let's say, closed systems that means that you have a speed of more than 1.5 meters per second. And of course, although there's not really theoretical justification, there is a maximum set of 2.1 meters per second. And also here, if you go too high, of course you can do that also, but it also means that you have to have a higher in energy cost. So stay between 1.5 and 2.1, and then you're on the right side. Looking at a manual application of cleaning, and of course that's not really the CIP, but sometimes you have to do a manual cleaning. Brushing, of course, is very subjective because it depends much on who's doing it, but it's possible. A third way of having mechanical energy is high pressure, mostly done to clean surfaces, ceilings, etc., or floors. Steam can be applied, but it might be dangerous for the personnel because of the high temperatures. And then finally, time. If you have time enough, of course you can wait, because also time is doing its work. But of course, every production company wants to have a less cleaning time as possible. So therefore you want to decrease that as much as possible. And that's also one of the issues we work on during the CIP optimization. How can we reduce time so that we have more time available within a production process? But of course, if you have the weekend to soak, that's always a possibility to look at. Okay, so far the cleaning parameters. Now switching to disinfection. Before we start, actually disinfection within a good CIP protocol, within let's say standard food production, should not be really necessary, because it's actually good to keep in mind that a good cleaning process already results in a 90% reduction in microorganisms. And even if you have an 80 degrees C 1% alkaline solution, it even is effective against spores. So in that case, if you do a very good cleaning, yes, disinfection can be done. But if you keep in mind that after cleaning you will go to work, let's say raw products or raw milk or other raw products which contain already, let's say 1,000 or 10,000 bacteria per mil, then you should wonder whether it's really necessary to have very clean equipment. Of course, if you have a good clean equipment, then you have already very low concentration, that you should ask yourself, is it disinfection really necessary? So therefore we see that disinfection, especially for, let's say, sensitive processes, so where you don't want to have any risk of recontamination, or when no high temperatures can be applied during cleaning. And for example, for membranes that's possible. What's also thinkable is when you have contaminated water supplies, that you want to disinfect your water in this particular case. But again, go back to the disinfection process itself. There are a couple of means that can be applied. First, you have, let's say, the so-called physical disinfection, and it could be heat or steam, UV, gamma irradiation that can be applied to let's say, to inactivate or, let's say, reduce the amount of bacteria. What we do see is that, especially for the dairy, that we mainly see, let's say, a chemical or let's say, I should say the other way around. Looking at a chemical way of disinfection, we do see it relative for dairy, and later on I have an overview of different, let's say, means, different chemicals that can be applied for chemical disinfection. Then you have two ways of doing so. First of all, you have the circulating way of disinfection, meaning in fact the same as CIP. So you start pumping around, let's say, disinfectant, and for example halogens, or let's say the peracetic acid or the hydrogen peroxide are very known for their application within this type of disinfection. More, let's say, disinfection out of place, and then we talk about soaking or spraying. You see more the iodophores or the quaternary ammonium compounds that are applied, for example, to disinfect surfaces. If you don't have the possibility to do it, let's say, like a disinfection in place, you do it like a disinfection out of place. As I mentioned, this is the table I was talking about. You do see here a couple of applied disinfectants, and on the bottom you see that the source is from a chapter I wrote a couple of years ago. It gives an overview about the type of disinfectant, and we start with, let's say, the halogen releasing agent, for example the chlorine or the iodine, further to peroxidants, alcohols, etc. And you do see here the concentration they're normally applied. And you see in the third and the fourth column, you see the bactericidal and the sporicidal concentration. And that's something to explain. Bactericidal means that it works against vegetative cells. So vegetative cells are normally less resistant against all these kind of disinfections, whereas the sporicidal concentration is much higher. And in some cases, some compounds do not work against spores. For example, the quaternary ammonium compounds, they do not work against spores. So it's very important to know, if you do have spores in your environment, don't apply the QACs or the bisphenols. For example, chlorine is known to be very effective, and it's also important to know that for chlorine, no resistance is built up. So normally bacteria are known that they can adapt to their environment, but in this case for chlorine, they normally do not have a, let's say, resistance build up, whereas for other means it happens. So to just a very short revisiting of the Sinnen circle, I made some changes about it. and you'll see later on why. First, we have the temperature, and it's very important to avoid very high temperatures and adjust the time temperature vary to the location that are easy to clean. Time, reduce product equipment contact, so do it as short as possible. Looking at chemicals, very important, as I mentioned, to choose the right chemical and not too high concentrations. And beware also if you apply, for example, chlorine, it can be corrosive to your stainless steel. So if you apply it, be sure that you rinse it away very properly. Mechanical action, as I mentioned, make sure that you have a high velocity to have a, let's say, a turbulent flow. What you do see is that, for example, ultrasound or back flushing is applied in specific applications. For example, back flushing is done for let's say, for membrane cleaning. Finally, equipment, it's very important. What type of equipment are you cleaning? It says something about the design of the equipment, and we have some slides about it later in the presentation, so I'll not say anything about it. But smooth surfaces, no dead zones is very important to keep in mind when you design your production process. So for the process-related issues, when we look at the product, you do have the age of fouling. If it's very old, it will take more time to remove. And you have the matrix. So what type of fouling do we have? Do we have pathogens? Do we have proteins? Do we have minerals? So it's very important to choose your type of cleaning based on the type of fouling and not the other way around. So keep that in mind when designing your production or your CIP process. Well, knowing now a bit more about the cleaning theory, we now come to the CIP conditions. How should we design our CIP protocol? Looking at let's say, a standard CIP, we can distinguish a couple of phases. First, we do have a pre-rinse, so to remove, let's say, the big parts of the fouling, followed by a 1 or 2 phase cleaning. It could be alkaline combined with an, let's say, sequestering agent, or an alkaline followed by an acid step. And finally, if necessary or appropriate, you can have a disinfection step. It's very important to look at your water quality to start with. For example, if you have an environment where you have very excessive hardness, so talking about, let's say, above 15 degrees German hardness, it could result that you have an increased concentration, that you need an increased concentration of cleaning agent, because otherwise calcium soap has already been made, and meaning that your active concentration will be reduced. So you have actually an inactivation of your cleaning agent. Well, be sure that your pH is between 6.5 and 7.5, and please take a note of your microbial standards, especially when you have your own water source. Be sure that you have good clean water, and look at the mineral content. And a bit like the excessive hardness, look at the concentrations of the various minerals in your environment, and what will be in your water source. Well, something to mention about spray dryers. Spray dryers are known. Okay, if you want to clean a spray dryer, I would say, well, don't. If you can have a dry cleaning, do it. And in that case, you should be able to vacuum. So remove, vacuum the powder within your installation. If you do have to clean wet, and in some cases the type of tower, the cleaning tower, makes it necessary to do so, actually the way of cleaning is not different than from a standard CIP procedure. But what's very important that you do have step 6, which is drying with hot air. It's very important to get rid of all the water remainings in your production process, because the combination of dry powder with water will always result in extra contamination, extra growth of bacteria, because powder does contain bacteria that can start growing as soon as water is available. So it's very important, looking at salmonella, looking at spores, to get rid of this water in order to get control over your possible risk of outgrowth in powder. So if you can prevent it, the wet cleaning, do. If not, well, in that case, dry at the end of the procedure. Well, that brings me already to the, let's say, the typical CIP settings. What time is feasible? And we try to make, let's say, an overview of what is normally applied in practice. And please keep in mind these figures are based on specific product process settings, and depending on your situation, these times can change. But when you look at evaporators, plate heat exchangers, etc., looking at evaporators, 1.5, let's say, net cleaning time, 1 hour, 1.5 hour net cleaning time could be possible. But of course, if you very heavy fouling product, it could take longer. Plate heat exchangers, more or less the same. Normally 0.5 to 1 hour. Dryers, very important to mention when they are cleaned wet, of course. Depends a lot of the configuration of the dryer. Is it only a single stage, or do we have a multi-stage dryer? 4 to 8 hours minimum. And excluding the drying of the tower, it's very important to mention. Direct steam injection, DSI equipment, 1 to 1.5 hour, and membranes, yeah, depends a bit on the configuration again. They are a bit more difficult to clean and also less resistant against all types of aggressive chemicals. So it depends a bit on the type of cleaning component you use, but 1 to 2 hours should be feasible. What agent should be used? Well, in our practice we do see that just plain alkaline or nitric acid is very effective and also cheap. But in some cases you cannot avoid the application of what we call the commercial cleaning agent, and specifically when you have let's say more sensitive processes or equipment like membranes, yeah, you do see that you have to choose with these kind because they're designed and developed to work on the very, let's say, low temperature conditions, but and still have enough fouling removal capacity. Well, that brings me to the possibility of reduction or optimization of a cleaning process, and that brings me already to the end of my part of the presentation. But what we do see in our practice is that when you look very closely, very intensively to a standard cleaning protocol, an average of 50% reduction of cleaning time is normally possible. And not only cleaning time, but also the reduction of, let's say, the decrease of the concentration of cleaning agent. It's also very good to mention, and it also works. You can save, let's say, half of the chemical use, which is very important, especially from an environmental point of view, not only from a cost point of view, but also from an environmental point of view. But how to achieve that? How can we achieve a reduction of this process? Well, it's very important that you have a very good monitoring and control. And Martijn will now tell you about how to achieve that and what ways do we have to optimize our cleaning protocol. Martijn, the floor is yours.
Thank you, Arjan, and welcome everybody, also on behalf of myself. As said already, Arjan told a lot about the theory behind it and what factors are influencing fouling. I would like to go a little bit more into how to solve these issues and to show some practical examples. And before talking about optimization, I would like to tell a little bit about the NISO vision. And the first thing which I would like to mention is that you should just try to avoid fouling. If you have a longer run time and you run 24/7, longer run times means less cleaning, less energy use, less use of chemicals. Always better, I would say. Secondly, the optimization of the cleaning procedure. If you have equipment which is fouled, which you need to clean, then you can start thinking about how to optimize the cleaning procedure and how you can make that improve that based on the fouling at the outlet. And third of all, after you've improved or optimized your cleaning procedure and you looked whether not all the remainders of dirt have left the system, always check inside your equipment whether it's really clean. And of course you don't do that every time, but if you're doing an optimization, check it, since dead corners, specific spots which are not cleaned well, bacteria, mineral deposits, protein deposits, they can just remain over there. So usually we advise to apply a combined approach consisting of, well, first of all, predictive models to simulate your process and to look whether your process is doing the right things. In essence, to avoid fouling. Secondly, OptiCIP, to improve the cleaning procedure itself. And third of all, always look inside your equipment, so do a process scan. So to start with the avoidance of fouling, there are a lot of factors which are influencing fouling, and you can avoid them by adding processing aids. I will show an example, but you can also look at the composition of your product. Specific components are causing a higher fouling rate as other ones. You can think of optimizing a process itself. If you know about the fouling mechanism and the reasons behind it, you can also always think about how to improve it, and whether you can, well, for example, use different temperatures, different residence times, improve your process line, that way optimize your process. And predictive models are of a great help for that, as far as our opinion accounts. And third of all, use a hygienic design. Well, start with the processing aids, so the product properties. Something which is used more often in dairy industry is the use of polyphosphates. If you talk about, for example, about evaporators, they suffer from a lot of mineral fouling. This mineral fouling is actually calcium salts, calcium phosphate, calcium citrate, which is deposited on the inside of your evaporator tubes. Something which you don't want, since it reduces heat transfer. It limits the efficiency of your equipment. It can also serve as a matrix for microorganisms. And by the use of polyphosphates, you can retard the buildup of these calcium salts, so your runtime is longer, your evaporator remains cleaner in the long term. So this is one way to improve your process. Another example, a fruit dairy product, a combination of fruit with dairy. What we optimized over there was actually a process, and what we did is optimizing the time temperature profile. We used predictive models in combination with our practical experience, and by optimizing your time temperature profile, you can always it was possible to also optimize the amount of fouling, so reduce the amount of fouling and thereby increasing your runtime. And pectin concentration was an important parameter with that respect. As said, if you want to optimize a process, you should know something about the mechanism of fouling. And one way to think about fouling of proteins, dairy proteins, is to look at the protein beta-lactoglobulin. The way we look at it quite often from a mechanistic point of view is that beta-lactoglobulin is actually activated in a heating process. Means that the beta-lactoglobulin, you can see native beta-lactoglobulin on the left. In the middle is activated beta-lactoglobulin, and this activated beta-lactoglobulin can do two things. Either it will aggregate or denature and aggregate towards an aggregated beta-lactoglobulin protein. Not a big issue anymore, at least not from the point not with respect to fouling. Probably it's a product property which you would not like to have, but that's another question. But it can also aggregate with other milk components and form a deposit on the wall of a heat exchanger, of an evaporator, of other equipment, and form a fouling layer. Well, what we did was implement this mechanism into our process simulation platform called NISO-Premia, and Premia actually stands for Predictive Models for Industrial Applications. And well, the picture I show over here is a very qualitative way of showing it. We added kinetics to that. We said, how fast is this activated beta-lactoglobulin created? How fast is it depositing or denaturing and aggregating? And if you use this model in combination with the process settings, you can look what is happening within your process. This is implemented in our predictive model or in a processing platform called NISO-Premia. And Premia is actually a platform which is very well suited for the description of process-product interactions. On one hand, we have our process data, So for example, the residence in different steps in a heat exchanger. And you can see a picture over here where you see, well, a screen dump from NISO Premia for a heat exchanger. And you can see that you can really describe the heat exchanger into very large detail. So what kind of, do you have a tube heat exchanger, a plate heat exchanger, a flash vessel, are you having a heat treatment process in an evaporator? How many plates do you have? Are they parallel, in serial? What are the sizes, the dimensions, etc.? So you can really describe your process into detail. And I showed over here a heat exchanger, but we also have models for evaporators, spray dryers, but also for cheese processes, for example. On the other end, we have the microorganisms, the properties. So how fast are they growing? How fast are they inactivated by specific heat treatments? But you can also think of other product properties like the fouling, which I showed, or the protein denaturation. If you combine these things, the product data and the process data, you can really look what happens with your specific product within the equipment and how fast is, for example, your heat exchanger fouled. And actually, NISO Premia is containing more than 20 model units. And we use it a lot for debottlenecking or showing or pinpointing effects of your process on, well, whatever kind of property you would like to see. An example, probably that's the easiest to show it. We had a case and we're actually working on a confidential base. This example is, we're allowed to show it, was an infant food from Nutricia, now part of Danone. And they had a process in the past where they wanted to implement a new formulation for this Nutrilon neonatal, but the product was fouling heavily inside the heat exchanger. So you had a fouling rate of 340 grams per hour, and this was actually leading to run times of less than 2 hours, so not a feasible process. What we did some test trials in our pilot plant, combined the results of these test trials with a predictive model, within this NISO Premia, validated it by experiments, and we could optimize the process. So we got a new time temperature profile. We had the whole setup changed of the process, leading to a better designed heat exchanger process. And the nice thing about it, the fouling rate reduced from 340 to 120 grams per hour. Problem solved. In addition, the reduction of Bacillus cereus, which is an indicator organism for spore growth, was this reduction was 5 log reduction instead of 1, a huge increase. So a better heating process, and it's shown within the term HMF. It's Maillard products. They were formed quite heavily, so you got a little bit enough taste. And with these new process settings, you only had there was a reduction of these Maillard components, so your product properties themselves were also improved. Actually funny, you see that you want to improve your fouling rate. In addition, you improve more properties, and this is something which you see more often happening. Another example, improved spray dryer functionality. We had a producer of spray-dried infant food in Russia, and they had severe fouling problems. And the fouling inside a spray dryer is actually a high risk. I mean, a spray dryer, you have hot air, you have a powder, and if you would have a small spark, you have the ideal ingredient for a bomb. It can explode, and that's something you don't want. So try to avoid the spark, since the hot air and the powder are necessary for your spray drying process. Fouling can result in smoldering, so you can have lumps within your spray dryer which start to smolder, and the smoldering can result in explosion risks. So you should avoid fouling in the spray dryer. What we did, we visited the site, we modeled the spray dryer first within NISO Premia, then within the CFD, a computational fluid dynamics package, and there you can really model the whole airflow patterns inside the spray dryer. And we proposed improved conditions for the design of the air inlet. And actually, what you see is that by adapting the airflow, so improving that one, it led to first of all, less fouling, or less fouling, no fouling anymore, but the whole airflow pattern inside the spray dryer was improved as well, and it sounds very like a huge investment to adapt the airflow in the inlet airflow, but actually in this case it was a minor adjustment. Okay, it cost some money to adjust it, but it was not such a big deal. It was a small change of the design, and you had a better airflow pattern, better residence time distribution. The fouling problem was solved, and in addition, the powder properties themselves were also improved a lot. So once again, solving one problem leads to a better solution of other properties as well. Hygienic design, the third issue which I would like to point to. First of all, you should think about your process design. Is it hygienic? What kind of process do you use? What temperatures do you apply in this process? What are residence times? What kind of products do you use? Not that each product is fouling as heavily as the other one. What is the protein content quite often? But in the process, next to that, you also have the design of your equipment. What type of material do you use? Stainless steel. What kind of stainless steel do you use? 304 or 316? Do you use some plastics or others? And what surface finish do you use? At the right you see a graph. On the x-axis the roughness of your material given in millimeters. It's the RA value. On the y-axis it's the cleanability. So how good can you clean your process? A low value you can clean it very well. High value, very bad. What you actually see is that your process equipment should have a roughness of about 0.25 to 0.6 micrometers. Having a more rough surface leads to a worse to clean surface, but very interesting as well. A very flat, very nicely surface can foul more heavily than a little bit of rough one. So your roughness shouldn't be too low and too high. Both of them are actually not good. Be in the right region. And well, that's for the basic surface finish. Of course, something which you also we observe also quite often is joints and weldings and couplings. If you have a bad welding with a very rough inside, okay, that can be a start of fouling within your equipment. And then you can have a very nice, good stainless steel with a very good surface finish, etc. If your weld is not good, that's the start of troubles. You should also think of the design of the equipment itself, so avoid dead ends. At the right top you see a picture of actually a corner of piping with a dead end, and the blue depicts a region where you have a low flow velocity. So during cleaning you have a low flow velocity, and not all material or all fouling in the dead end will be removed that well. Moreover, your equipment should be drainable, so try to avoid a layer of water or remaining product or cleaning fluid or whatever inside your equipment. After cleaning it should be clean and dry, or at least no water or no product or cleaning fluid left inside the equipment. The materials should be suited for your cleaning regime. Try to avoid if your material is how do you say it? Is for example, if you have a steel which is corroded by your cleaning agent, your surface will become worse. So try be careful with the cleaning agents you use, and take care that your materials of your equipment can withstand it. Surface should be smooth. We talked about that already, and it should be easy to maintain. So try to have it easy accessible. And last of all, the surroundings should be clean as well. If you have very nice clean equipment, from the inside it can be perfect. If you have a lot of mess around it, you can wonder whether your product will remain clean. Take care that the surroundings, the factory, the plant itself is also clean. Try to avoid large amounts of dust, for example, as you see in the bottom picture. So, if you have a hygienic design, try to avoid wet biffs. Wouldn't it be nice if we add some equipment or add a nice piece of piping somewhere that we have the opportunity to do this and that. If it is not necessary, leave it out. Keep the equipment as well straightforward as possible. That's the next one. Keep it stupid simple, or keep it simple stupid. Keep your equipment easy. If there is a lot of fuzz around it, extra added options, it usually is a recipe for problems in the future. So, something about the optimization. If we have an optimal process, we would like to optimize the cleaning process itself. The tool we use is OptiCIP, and actually what we're doing, we're monitoring a cleaning cycle by taking samples at the outlet, registering all CIP conditions, which valves are used, etc., measuring in the samples how much fouling is removed. Based on that knowledge, optimize the cleaning procedure and do a second monitoring to validate it. A more advanced version is online monitoring, so inside your process equipment at the outlet of whatever kind of process, you have a specific piece of equipment where you're monitoring the amount of fouling removed, etc. continuously. You can connect it to your SCADA systems, and this way you can optimize it continuously and let that even be done automatically. So start with OptiCIP, the regular one. What we do is actually we have a cleaning cycle, and during the cleaning cycle, each amount of time, for example each minute, we take a sample. And in the meanwhile, we're logging all relevant data. So what is the temperatures we're using, which valves are open, are we adding acid, caustic, or whatever, are we adding water, are there any other important features to be logged. And these samples which we take every minute are analyzed on on turbidity, and this turbidity says something about the amount of organic fouling inside your equipment, so protein fouling. And the second thing is that we measure it on calcium content. Calcium tells something about the amount of inorganic fouling which is present inside your cleaning equipment. We take these samples at the end of a piece of equipment, so for example at the end of an evaporator or at the end of a heat exchanger, and you get a profile like shown here on the left. On the x-axis you have the time, on the y-axis the amount of fouling. We have this cleaning process. The yellow bar actually shows a part in the beginning where nothing is happening. Then we have an alkaline cleaning, followed by, well, some more time, an acid cleaning, and some more time. And what you see is two peaks, from 1 to approximately 2.5 hour time units. We see a peak of the turbidity, which is an indication that we have a lot of organic fouling removed over there. And from 4.5 to, well, 6.5 time units, you have the peak of calcium, which is actually showing that a lot of inorganic fouling is removed over there. Quite logical, actually. Alkaline cleaning usually removes organic fouling. Acid is very suitable for inorganic fouling removal. The interesting thing about these two peaks is that the left peak is quite wide. Ideally, you would just like to remove all your fouling at once within a very short time period, and that's it. The right peak, the acid cleaning, shows a quite sharp peak. Nice, just what you want. The only thing, there is a tail from, say, 5 to 6 time units. For quite a while, a small amount of inorganic fouling is removed. Ideally, you would only like to have this peak. So if you optimize it, you have a shorter alkaline cleaning and a shorter acid cleaning, only the peaks, no tails, and you can reduce a lot of your cleaning time a lot. Well, this optimization can be dependent on all kinds of factors. Increase flow rates, change your chemical dosage, look at which valves are working at what time, are there any intermediate steps which are, well, not very suitable for the process. That depends very much on the CIP process itself, so on the data which are also logged at during this cleaning cycle measurement. But this is the way the OptiCIP works. So know what happens when you're doing a cleaning. You can do it also in an automatic way, and the idea is that you measure inline turbidity and conductivity, and preferably also calcium content, but that one is a little bit more difficult to do. And you have a self-learning model-based cleaning control system. So this control system uses some predictive models for how much fouling do we get based on specific process settings. And this computer knows what the processing settings of the product to be produced were during the last day, for example, or a few hours that the process was running. It has a historical database, so it knows at what time or what kind of product and what composition results in what kinds of amount of fouling. And during a cleaning, it can measure whether really all the organic or inorganic fouling is removed based on the sensors. Using this completely automated control, we estimated an annual cost savings in one pilot project of 180,000 euros a year, meaning more production capacity, reduction of energy, water, and fouling equivalents. We've optimized our process, we've optimized our cleaning procedure. One thing remains: always check it from the inside. For example, evaporators, well, they're nasty pieces of equipment, a lot of dead corners, spots which are not cleaned very well. Really look inside whether everything is clean, yes or no. We do that by a process scan. Usually the production site is visited by NISO experts. We're looking at the inside, check everything. Also look at, spots where you would expect things to go wrong. Look at the fouling, the running performance, so you can also, these process scans usually we also apply them to optimize the process itself, so to trying to avoid the fouling. And you take relevant samples to analyze and to look what kind of fouling, for example, you have. At the bottom you see an XMRA spectrum of fouling. Well, that's one technology to use to look what is the composition of your fouling. And if you know what the composition is, you can start thinking about solutions. Combining this all, you can define measures to quantify them with a relevant budget and to look whether it's doable to improve this CIP process, yes or no. It's always a budget case. You have to invest. You have some savings. Is the savings more than the investment? That's the thing you have to answer. So, resumed for this whole webinar. First of all, know your enemy. What fouling are we talking about? Microorganisms, protein fouling, inorganic fouling, mineral fouling. What is the composition of this mineral fouling? What kind of microorganisms are we talking about? What kind of equipment are we using? First, define the battleground. If you know that, then you can start thinking about solutions. You can, if you talk about the cleaning parameters, as Arjen told, too much is not always better. Adding more caustic or alkaline is not always a better solution. Commercial cleaning procedures are products. They're good for special purposes like membranes. You can use them for other in other situations as well. It's a cost issue, and you have to decide for your own whether you want to use them or whether you stick to regular alkaline or acid. With regard to disinfection, really determine a need to do it. Disinfection is not always necessary, and in quite some cases we have the opinion that a good cleaning procedure itself should be enough. But I know there are cases where you really want to be sure, and there you should do a disinfection. And in dry environments, try to do a dry cleaning and try to avoid wet cleaning as much as possible. Your design should be based on needs and knowledge of the process. So think about your fouling behavior while designing a process, and don't do it afterwards when you build your plant and you're trying to solve the problems, since changing an existing configuration is usually a much more effort than doing it in advance. Prevent fouling. So know what your fouling mechanism is. This can extend runtimes and less cleaning in general, so less use of chemicals, energy, etc. If you've prevented the fouling, then you can start cleaning, optimizing your cleaning procedure. So collect data of the cleaning procedure, get insight in your efficiency of your CIP procedure, optimize your setting, and reduce the cleaning time. And also always check the inside. Some new developments are model-based cleaning, the OptiCip, which I showed, and well, we're still looking for the best calcium sensor, or the best sensor of calcium detection, to follow that one in line as well. But we have some troubles with finding a good one for really 24/7 industrial application without having any giving problems. But these are developments within cleaning. So that leaves me to thank the whole team who made this webinar possible. First of all, René van der Meulen and Maartje van der Vlier and Hendrik Prins for all the marketing and the technical things related to this webinar. Our CIP team, Rita Allesma, Gert van Houwelingen, Koen Akkerman, Rina van Heekesen, and many others. Thank you, team. And this leaves the webinar for us. This is what we wanted to tell you. If you're interested, feel free to contact NISO. Thank you.